I'm Ignacio Lopez-Gomez. I'm a PhD student at CalTech, working with Tapio Schneider for another week. Anyway, I'm graduating next week. And today I'm going to be talking about a framework for unifying turbulence and convection parameterizations, which we call the extended EDMF scheme. So the problem that we are interested in here is the persistent bias in low cloud cover in climate models. And this is shown here for one of the models from the CMIP6 ensemble. You would find similar biases in most other models. And the biases are particularly important off the west coast of continents in the subtropics. This is where we have regions of stratocumulus to cumulus transitions. Here, the low cloud cover biases can be as high as 50%. And this translates to fluxes in relative biases in relative fluxes on the order of tens of watts per meter squared, which are significantly larger than the magnitude of the anthropogenic forcing signal that we're trying to understand, which is on the order of 3 watts per meter squared. And so the way that this problem ties back with the topic of the talk is that we know that biases in many of these regions are caused by an imperfect representation of turbulence and convection in current climate models. So what does a typical turbulence and convection model look like? So here I'm showing a slice or an atmospheric column in a GCM. And what we typically have is a turbulence scheme that is active within the boundary layer. And as we cross the inversion layer, we substitute that turbulence scheme by a convection scheme. Most convection schemes are based on the ideas put forward by Arakawa and Schubert in 1974, where most of the convective transport is modeled in terms of convective updrafts, convective moist updrafts that are doing most of the transport. And so in this layer of the atmosphere, there are typically some trigger functions that we evaluate, and depending on that, on whether that trigger condition is met or not, we would have tendencies that come from fluxes from deep convective parameterizations or fluxes that come from shallow convective parameterizations. And so one of the problems that we have right now in current climate models is that we have independent and discontinuous parameterizations with empirical triggers for different processes. And so these the assumptions that underline these parameterizations and their interaction start breaking down as we go to finer and finer scales. And so one approach that can be taken instead is the one that was proposed by EDMF schemes in the first decade of this century and has been developed since, which is the idea of substituting the flow in the same structures from the ground up. And so we have within the boundary layer, we still have updrafts. In that case, model dry convection. These updrafts interact with turbulent fluxes in the environment throughout the column, and we just have a switch to we just have an evolution to moist convection, to moist shallow convection, or moist deep convection, depending on the updraft properties and the termination height. And so what we end up with is a uniform or unified continuous formulation across levels of these processes. Some other interesting properties of this scheme is that it allows us actually to model turbulence and convection interactions at the subgrid scale, not only through the grid scale. So for instance, the turbulent fluxes within the environment might depend on the properties of the updrafts. And similarly, we can have interactions from the turbulence through entrainment injection in the updrafts. And in the scheme, in the extended version of the scheme, we also have the possibility of modeling convective memory. So we are carrying prognostic equations for the properties in the updrafts and for the mass-flux, so that in the end we can, with one single scheme, we can model both shallow convection, deep convection, and turbulence. And so this framework, of course, doesn't close the subgrid scale modeling problem. We still have some processes that we have to parameterize. And so in this case, two important processes are the mixing length that defines the turbulence intensity within the environment, because we take the eddy-diffusivity to be proportional to the mixing length and to the square root of the turbulence kinetic energy, which here I denote as E sub naught. And we also need parameterizations for the entrainment and detrainment processes. And these are the ones that are going to essentially allow us to have a single parameterization for shallow and deep convection. Now, in terms of the eddy diffusion parameterization that we have, we use a turbulent mixing length model that is based on a local balance between production and dissipation of turbulence kinetic energy in the environment. Now, this is something that is empirically based on observations in isotropic and stratified environments, as we can see from observations. And what we're going to assume is that this balance is only broken in cases where there are constraints in the atmospheric flow that are forcing dissipation of turbulence kinetic energy. And in this case, we consider two sources of such dissipation. The first one is the distance to the wall. So of course, if we're 5 meters above a wall, we cannot mix more than 5 meters, for instance, and this causes extra dissipation. And we're also going to consider the dissipation that is enforced by stable stratification in the flow. And so in the end, we will construct a mixing length model that is a soft minimum of these three parameterizations or these three diagnostics. Now, we've evaluated our model at different resolutions for different cases that show large biases in climate model. So here, I'm showing the results for the potential temperature profiles and horizontal velocity profiles from our model, which are shown on several lines, and compared to the dashed or the shading, which is the spread from an LES intercomparison study. And we see that our turbulence model in this case, is able to reproduce the low-level jet and the stratification in the Arctic with vertical resolutions as coarse as 50 meters in these lower levels of the atmosphere. We've also seen that our turbulence scheme is the mixing length that we use is crucial for our scheme to actually be able to capture the strong inversion that we find in the stratocumulus regions of the west coast of continents. And so here we show, again, results from our EDMF model compared to LES and the shading from LES. And in the orange dots, you can see observations from an observational campaign of the coast of California. And here, again, we obtain good results that are robust to resolution changes up to 75 meters in resolution. Now, these two dynamical regimes are very influenced by the turbulence parameterization that we have in our scheme. But of course, the entrainment parameterization is crucial if we want to capture shallow and deep convection with the same scheme. And so the entrainment scheme that we have is based on work by Cohen-Doll. And here we take the entrainment and detrainment fluxes to be a function of relative differences between buoyancy and relative humidity between the subdomains. And here it's also crucial to have an accurate coupling between microphysics and the EDMF scheme. And so what we can see is that with the same model that we were using for stable boundary layers in the Arctic and for stratocumulus clouds in the subtropics, we can actually capture well the vertical structure of deep convection over the Amazon. In this case, this is the TRIM LVA case study. And we can also capture the timing of deep convection with the same scheme. And so these are, of course, results for individual cases that are based on canonical case studies. And now we're moving to less canonical cases. So we have a growing library of GCM-driven large eddy simulations that we can use to validate and further train our scheme. And so here I'm just showing results for different CF sites that are shown on that map at different seasons for our LES. For the LES and for the EDMF model. So we can see here that as a function of stratification, as a function of the decoupling parameter D, as we go from stratocumulus clouds to cumulus clouds, we are able to capture the dependence of cloud fraction and liquid water path on the dynamical regime. And we are able to do so significantly better than the GCMs that we use for the forcing, which are here on the black line. And so that's the end of the results that I wanted to show. So some of the conclusions are that with the extended EDMF scheme, we're able to provide a unified turbulence and convection modeling framework. We've also seen that a wide range of regimes that we've tested can be represented using generalized closures without having to resort to switches in our scheme. And then as we have more and more data coming from large eddy simulations and satellite observations, we can reduce the remaining uncertainty by using data-driven closures and objective calibration. And this has been shown recently with more large eddy simulations in this study. And so with that, I'll take any questions. Thank you.
Questions? Dave?
You weren't mostly addressing, say, the reflected solar from shortwave here, but there was the paper by Koshiro et al. On estimated cloud top containment index and its effect on low cloud feedbacks that must have been in your sort of area of target interest.
Right.
Give indications on what beyond inversion strength and moisture difference at the inversion might account for cloud cover when you're talking about a low cloud feedback?
Yeah, that's a good question. So actually, when I was trying to make this plot, I was trying to choose the x-axis that gave me the best transition from stratocumulus to shallow cumulus. And so here D is actually just the logarithm of the Brederton and Wyant parameter from 1997. I also tried the ECT parameter, so this entrainment index, and it didn't give me such a good stratification. And so I think that from that, our results suggest also for the LES, which we consider resolved, that metric wasn't as good as at separating regimes as, for example, this one. So it's a good question whether, I don't know which one is the best for all cases. At least for us, this one was the one that worked better than ECT or the estimated inversion strength or the LTS. Yeah.
Okay, I may have missed it, but are your turbulence statistics or your convection statistics affected by the horizontal mean wind?
Horizontal mean wind. So they are, but the problem right now is that, so all of these cases right now have, we have a periodic single column. And so they're not affected by horizontal convergence or divergence.
Right, but in like a stratocumulus and cumulus transition, that could be.
Yeah, so we do have, in the forcing, we do have advective forcing, horizontal advective forcing, yeah.
Thanks a lot. How would this work over land complex terrain? I mean, these are over oceans, pretty homogeneous.
Yeah, that's a good question. So we want to, so what we're trying to do now is just creating a larger library of large simulations over different conditions. So right now we've targeted this over the ocean because that's where the largest biases are. But in the end, I think we want to also test this over land. So I think we have a case or two over land, but they don't have any kind of complex topography, so we don't know yet.